All right, guys, welcome to your fourth video lecture. This one is going to be over two important theorems that you're going to learn this year in calculus. You're going to learn 5 theorems overall, but the goal of this lecture is to introduce you to 2 of them. Okay, the first one is called the intermediate value theorem, and I'm not going to read the theorem to you word for word. I'll let you do that kind of on your own, but I want to just kind of give you the main idea of what the intermediate value theorem is saying. So here's a basic example that kind of illustrates the intermediate value theorem. Okay, so let's say that in the morning you wake up at 8 a.m. and when you wake up, it is 62 degrees. Now, I don't know if that's going to happen necessarily during the summer. I hope it does, but I really don't think so. But hopefully it does. And so let's just say 8 a.m. you wake up 62 degrees. Let's say that currently, which right now it's 9:41 a.m. according to my iPad there. Let's say that at 9:41 a.m. the temperature had increased up to 71 degrees. What the intermediate value theorem is saying is that at some point in between 8 o'clock when you woke up and 9:41, which is the time right now, it had to have been 67 degrees at some point. It also had to be 68 degrees, it also had to be 69 degrees, and it had to be every temperature in between 62 degrees and 71 degrees. And the reason for that, the main reason for that, is because temperature is a continuous function. Okay, so because temperature is continuous, it can't just jump around temperatures. You can't just go from 50 degrees 1 second to the next second 75 degrees. It had to go through every single degree in between whatever your 2 endpoint degrees are. Okay, so that's kind of the basic idea of the theorem, and now I'm going to show you kind of how to use it to answer a problem. Okay, so the main hypothesis of the intermediate value theorem is that the function is continuous. So anytime a function is continuous, that is when we can use the intermediate value theorem. Okay, so example 1, train A runs back and forth on an east-west section of railroad track. Its velocity, which is measured in meters per minute, is given by a differentiable function v sub a of t. Now, the reason I highlight differentiable function is because what I need you to know about this word differentiable is that anytime you see that, it means that the function is also continuous. And we'll talk more about that during the school year, but for right now, you need to know if a function is differentiable, that implies automatically that it is continuous. Okay. So we continue reading the question. It says, do the data in the table support the conclusion that train A's velocity, and remember that's the function that we were given, is negative 100 meters per minute at some time t with 5 less than t less than 8. Give a reason for your answer. Okay, well they gave me an interval here to consider. So if I look at this table, the time values between 5 and 8 is this interval right here. And so the question is, does the velocity of train A have to equal negative 100 meters per minute at some time in that interval? Well, if you think about it, negative 100 is in between 40 and negative 120, and we already said that this velocity function is continuous because it was differentiable. So the answer to our question is yes. And so what we're going to say when we answer this question is, first of all, we're going to say yes because we have to state the hypothesis of the intermediate value theorem. So we're going to say because VA of t is continuous, and the reason that we knew it was continuous is because the original problem said that it was differentiable, which implies continuity. Because VA sub t is continuous and negative 120 is less than negative 100, which is less than 40. So that's me basically saying that the value that you want the velocity to be equal to, negative 100, is in between the 2 given velocity values at the endpoints of that interval. Then what we say is by the IVT, and it's okay for us to abbreviate the IVT, there exists a time t. Now, the only kind of tedious part of these problems is that they do kind of take a little bit of time to write out the answer. Though there exists a time t on the interval from 5 to 8 such that v sub a of t is equal to negative 100. That is a well-constructed sentence that answers the question, talks about the hypothesis of the intermediate value theorem, which is this part right here and also this part right here. Those are the two things that you need for the hypothesis of the theorem. And then basically what I do after I state the hypothesis is I really just kind of restate the question by saying there exists a time t, 5 less than t less than 8, such that v sub a of t is equal to negative 100. Okay, so example 2, again, just using the intermediate value theorem. It says a car travels on a straight track. During the time interval from 0 to 60, the car's velocity is a continuous function. So I want to make sure that I recognize I am dealing with a continuous function, and that means that the IVT applies. For 0 less than t less than 60, must there be a time? That is a very important phrase right there, must there be a time? I want you to get into the habit. Anytime you see that phrase, you need to think about using either the intermediate value theorem or the mean value theorem, which we'll learn here in just a second. So must there be a time t when the velocity is equal to negative 5? So what I do is I scan my table and I see, is negative 5 in between any of the velocity values given on the table? Okay, well, if I search through here, from 0 to 15 on the t-axis, the velocity goes from negative 20 to negative 30. Well, negative 5 is not in between those. So I know that there doesn't necessarily have to be a time when the velocity is equal to negative 5 on that interval. Now, could there be? Yes, because we don't have all of the information on the table, but there doesn't have to be based on the information that is given. Okay, I continue searching from negative 30 to negative 20, no. From negative 20 to negative 14, no. Negative 5 is not in between those. From negative 14 to negative 10, no. From negative 10 to 0, this is kind of the first opportunity I see for the velocity to equal to negative 5. Okay, so there is one instance, and then there's also another instance here, or is there? No, there's not another instance. Between 0 and 10, negative 5 is not between those, and so the only instance is going to be this interval right here where the velocity had to equal negative 5. Okay, so we are going to answer the question here by saying yes, since v of t is continuous, and that was given in the problem. It said that v of t was a continuous function, and negative 10 is less than negative 5, which is less than 0. So that's me saying that the velocity that you want me to prove, negative 5, is in between two of the given velocities, negative 10 and 0. Make sure that you state the theorem. So by the IVT, there must be a time. Okay, and they call it t, so we'll call it t as well. And that t is going to be between 35 and 50, because if you look back at the table, 35 and 50 were the t values for that particular subinterval. So between 35 and 50, such that v of t is equal to negative 5. Okay, that is a perfectly well-justified answer, and has everything that you need in there. So when you get to the assignment, make sure that you model after me how to justify your answer using the IVT.